Hi everybody. Welcome to the lesson in which we look at our next hypothesis test, which is comparing two means. So in this hypothesis test, we're going to suppose we've got two different groups, and we want to compare those means to each other. Now, in life, you may have noticed that when we have a lot of different words for something, that's an indication that that concept is important. And here you can see we've got three different terms that are all used for this hypothesis test. It's sometimes called the two-sample t-test. You'll sometimes see it called the independent samples t-test, or sometimes just the t-test. When people refer to the t-test, they usually are talking about this test as opposed to the one-sample t-test. Indeed, in this case, this is a very important hypothesis test in research. You can imagine there are a lot of times when you might have two groups that you want to compare. So, just like before when we were looking at the one sample case, there are three possible sets of hypotheses. For these, we've got the mean of group 1, we're calling mu1, and the mean of group 2, we're calling mu2. And of course, just like before, mu is the population mean, so we're comparing the two population means to each other. So the null hypothesis is always that the two group means are equal to each other. And the alternative hypothesis could be that one of them is less than the other one, or that the first one is greater than the other one. Or we could have the two-tailed case where they just differ from each other. And if you remember, these other two are called the one-tailed hypothesis test. So here's an example. We've got two groups of high school students who are going to take the SAT, and we're going to ask one of the groups, 25 in each group, one of the groups is going to eat breakfast before taking the test, and the other one is not going to eat breakfast. And we look at the results, and when we get those results, we find out that the group that ate breakfast had a mean score of 438 with a standard deviation of 49, and the group that didn't had a mean score on the math part of the SAT of 418 with a standard deviation of 56. So we want to test whether the students who eat breakfast have a higher score on average than those who don't. Because that's what they always tell you, right? When you go to take a big test, eat breakfast, at least that's what they always told us. So to run this test, we're going to go over to SPSS, which I've pulled up over here. I've got a data set up, but we're not going to use that just yet. So just like before, we're going to analyze compare means. And there's two options here. There's the independent samples t-test, which we're going to use when we have data, and we'll get to that in a minute. But what we have is summary data, where they give us the mean and the standard deviation and the sample size for both groups. So this is what we're going to use right now, the summary independent samples t-test. And so we just have to input the information they gave us. So the number of cases they said was 25 for both of them. The means we said was 438 and 418. Double check that. 438 and 418. The standard deviations were 49 and 56. And they give us an option to type in labels for the two groups. So group 1 was the people who ate breakfast, and group 2 was the people who skipped breakfast. Okay. All right, So we're going to click OK and wait for this output to come up. And we get 3 tables here. At the top, they're just repeating the information we typed in. At the bottom, this table isn't important for us. In the middle, this is what we want. This is our independent samples t-test. And I've copied the output over here so we can see it a little better. The first thing I want you to notice is that there are 2 rows of results. And here, most of it's the same. It won't always be that way. We're going to use always the equal variance is not assumed option. This is just a technical detail of how they're calculating the test statistic. So don't worry about that. Just always use the equal variance is not assumed option. So what we want here is, this is our test statistic, 1.344, so we're going to list that. And over here where it says sig two-tailed, this is our p-value. This is the p-value for a two-tailed test. So if you're doing the alternative hypothesis of not equal to, it's going to be 0.185. This is one of those things that that's kind of a carryover. I know I told you that that SPSS had updated some of the way they write output, but this one hasn't been updated yet. So this one is still going to be sig two-tailed is your p-value for a not equal to alternative hypothesis. And this means if you want a one-tailed alternative hypothesis, you're going to need to divide that p-value by 2. All right, so you're going to have to look at up here which way this goes, just like we did before, where we're looking at the mean of group 1 is bigger than the mean of group 2, and so that means if you want to do a one-tailed test, that's going to be looking at whether the population mean of group 1 is bigger than the population mean of group 2. And that's what we want for our hypotheses. So our hypotheses are that the 2 group means are equal to each other. And you can write, if you want to write these as breakfast eaters versus breakfast skippers, instead of 1 and 2, you can write eat and skip or something in there. But our hypothesis is that people who eat breakfast have a higher score on average than people who skip breakfast. So from that output, we see that our test statistic is 1.344. Our p-value is 0.185 divided by 2, so 0.0925. And we said we were using 0.05 for our alpha. So as always, our rejection rule is reject H0 if p-value is less than alpha. This p-value is not less than 0.05, so we are going to fail to reject H0. And since we're failing to reject H0, it means we have not been able to conclude that on average people who eat breakfast score higher than those who don't. So we talked about the effect size for a one-sample t-test, and every hypothesis test that we talk about is going to have an effect size. So for the two-sample t-test, it's again going to be Cohen's d. And in this case, Cohen's d is going to be calculated as the difference in the two sample means. And you're going to take the absolute value. SPSS doesn't do that, but I want you to take the absolute value of the results. And we're going to divide that by the larger of the two group standard deviations. Now, just like before, the rough guidelines are 0.2 is small, 0.5 is moderate, and 0.8 is large. But again, I want to emphasize that in the real world, you're not going to take these and just kind of blindly pick the closest one. You're going to compare to similar studies. You're going to think about the context of the data to help interpret this. So in our example, we had the sample mean for the people who ate breakfast was 438. The sample mean for the people who skipped breakfast was 418. And if we look at the two standard deviations, the larger of the two was 56. Okay, so the people who skipped breakfast had a larger standard deviation, which was 56. And so when we do that calculation, we do that right here. So 438 minus 418. And remember your order of operations, so make sure you do that top part first. And then divide by 56. And we get 0.3571. So remember, this tells us that, so we're going to interpret that in conjunction with the hypothesis test results. So we can't conclude that people who ate breakfast have higher scores on average, but if we could, that difference would be moderate. Okay, because this is 0.35, which is in that moderate range. So that's closer to moderate than small. You could call it small to moderate if you want. All right, so that's our first example of a two-sample t-test. I want to take a sec and just explain why we're choosing the larger of the two group standard deviations. So there are some different ways we could do this. We could take the smaller of the two, or we could take the larger of the two. We could take the average of the two. We could do like a weighted average based on the sample size of the two. We're just going to pick the larger. If we had to pick the larger or the smaller, we're going to pick the larger, because if you pick the smaller one, this is going to be a bigger number than if you pick the larger one. So if you put the bigger number in the denominator, this is going to be smaller. And if you remember when we were talking about type 1 and type 2 errors, we said we want to be careful and not overstate our results. And so we want to choose the smaller of the two possible sample sizes, or two possible effect sizes, if we have a choice. So that's what we're doing. We're trying to make sure that we don't overstate the value of our results. So we're choosing, we're erring on the side of caution here. So now let's look at a different example. In this example, we've got a data set called attention span, where we've got a bunch of data for teenage males and females on different aspects of their lives, including attention span, how much TV they watch, etc. And what we want to do is we want to compare the mean amount of time spent watching TV for the males versus the females. So here's our data set. We've got the gender of the teen, and then this other information about them. It's important for us to make a note before we go on. We're going to need it in a minute. That in this data set, 1 represents males and 2 represents females. No matter what your grouping variable is, and that's what this is here, gender is our grouping variable. That's how we're going to define what our two groups are. We're going to need to tell it what those two numbers are. So 1 represents male and 2 represents female. And by the way, SPSS requires that these be coded as numeric. You can't just use female and male, because if you do, it won't run the two-sample t-test. So we've got those coded as 1 for males and 2 for females. So we're going to go to run this test. It's again, analyze, compare means. And this is the independent samples t-test, not the summary one. This is just the plain old independent samples t-test. And the variable we're interested in looking at is the number of hours per week spent watching TV, so that's our test variable. Our grouping variable we said was the gender. That's our, we're comparing across genders, so we're putting that over there. And you see these question marks here, that's telling us that it's waiting for us to define groups. And so we looked up, before we came over here, we looked to see that our two groups were represented by 1s and 2s. So we're going to leave that as 1 and 2 and click continue and click OK. And you see in our output over here we get 3 tables. The first one includes our summary statistics. The next one is the results of our hypothesis test. And then the third one is going to list our effect sizes. So I've copied these over here so it's a little bigger, and I've put some notes on here for you. So in the top, you see our summary statistics. So, and I may ask you to discuss these, and if I do, here's what you would say. You would say, from our sample of size 22 males, we get a mean amount of time spent watching TV of 7.7045 hours per week, with a standard deviation of 3.82 hours. And from the sample of 18 females, we get a mean amount of time spent watching TV of 11.1389 hours, with a standard deviation of 4.90 hours. And I'll point out here, just because this is our first example where we don't have the same sample size here. And I want you to know that's okay. You don't have to have the same sample size for both of your two groups. That's not an indication that something was wrong. So in our output here, just like before, we had 2 rows. We had equal variances assumed and equal variances not assumed. And we're going to use the equal variances not assumed row. And I put a big X here because there's this extra test here, and we're not going to use it for anything. This Levene's test for equality of variances is not anything of interest to you, so please just avoid it. So we come over here, and over here is going to be our p-value if we're doing a one-tailed test. And this is going to be a lower-tailed test because Group 1 has a lower mean than Group 2, so we're going to compare in our population whether Group 1 has a lower mean. And then over here is going to be our p-value if we're doing a two-tailed test. Remember, a two-tailed test is not equal to. And then down here is our effect size. Make sure you're using Cohen's d and not one of these other ones. If you were to calculate by hand this Cohen's d, you'd get a different value. And you see here that's because Cohen's d is using what's called a pooled standard deviation. It doesn't really matter, but they're using the weighted mean. They're doing the mean standard deviation weighted by effect size. But all you need to know is here's Cohen's d. So let's first run a two-tailed test where we just want to know, to start off with, is there a difference between the male and female amount of time spent watching TV? So if we do that, our hypotheses are going to be that mu1, so mu for the males, is equal to for the females versus not equal to, because that's the two-tailed scenario. So if we get our test statistic, that's going to be -2.429. And our p-value is going to be, for the two-tailed test, 0.021. That was 2.829. So we get that from the output. And we're going to, as always, reject H0 if the p-value is less than alpha. Alpha in this case, we're using 0.05. And here our p-value is less than alpha, which means that we are going to reject H0. So we're rejecting H0, which means we can conclude what's in the alternative hypothesis, which is that there's a difference in the means. So now if we want to do our effect size, we were looking at this output. They listed as negative 0.792. We're taking the absolute value. So that's 0.792, which is in that large range. 0.2, 0.5, and 0.8 was considered large. So 0.792 is pretty close to large. So we are able to conclude that there is a difference in the means, and it looks like it's a large difference in the means. What if now we wanted to run a one-tailed test? And remember, if we're looking at this output, in the sample, males have a lower amount of time spent watching TV, and females have a higher amount of time spent watching TV. So let's run a one-tailed test. So if we're doing the one-tailed test, we're going to be testing whether males watch less TV than females. So we're going to run this as a one-tailed test. And one thing I want to point out here is that you can phrase this as teenage males watching less TV than teenage females, or you can phrase it the other way around, saying females watch more. And just be careful about the alternative hypothesis here. Just because you see the word more here doesn't mean this is greater than. So you have to look at, here we've got males as 1, females as 2. So we're saying males watch less than females. So again, from our SPSS output up here, we got 2.429. I'll fix that value. Our p-value for the one-tailed test was 0.01. And as always, we're rejecting H0 if p-value is less than 0.05, and then nothing else from here changes. So our p-value is still less than alpha, so we get the same rejection rule and the same conclusion. And our effect size doesn't depend on whether this is one-tailed or two-tailed, so we get the same effect size and the same interpretation on the effect size. So let's look at another example. This will be our last example. So we've got this oatmeal company who thinks that if you eat oatmeal every day, that's going to be better for your cholesterol than even taking a drug. There's a whole class of cholesterol drugs called statins. Ask me how I know that. So we're going to take, to test their hypothesis, we're going to take a sample of people, all of them who have high cholesterol, and we're going to randomly assign them to either eat oatmeal for a year or take a low dose of this statin drug. And here our sample sizes are not the same, so some people dropped out, and like we said, that's totally fine, that's not a problem. And each data point in here represents, this means that the person's cholesterol dropped by 12 points that year. This one dropped by 19 points, etc. So I entered that into SPSS, and it might be tempting to input that as, the cholesterol in one column and the cholesterol for the people who ate oatmeal in one column and for the people who took the drug in another column. But SPSS needs it in this format where all the cholesterols are in one column and then this grouping variable is in the other column. So we're going to do just like we did before. This is going to be compare means, independent samples t-test, and our test variable, and you've got to remember the difference here. The test variable is the thing we want to compare. So this is going to be our numeric variable. And the treatment group, this is always going to be our categorical variable. And then under defined groups, I put those in as 1s and 2s. So click continue and click OK. And you can see over here where if you look in the value labels, those are 1s and 2s. So here's our output, which I've copied over here. So our hypotheses are that the oatmeal group is going to have a higher mean than the drug group. And I realize this one is a little bit strange because we're saying which one is lowered more than the other one. But the way these numbers are, these numbers represent the dropping. So bigger numbers here would represent better results. So here we want to know if oatmeal has better results than the drug. So this one's going to be one-tailed. And you can see here, looking at equal variances not assumed, we have a test statistic of 2.908, and our one-sided p-value is 0.004. And that's 2.908. And that's going to be wrong on all of these. But regardless, we're going to reject H0 if the p-value is less than 0.05 because we're testing at the 0.05 level. This p-value is less than 0.05. So we are going to reject H0, which tells us that there is sufficient evidence to conclude that oatmeal is going to have better results than this statin drug on average. And if we look at our Cohen's D is 1.13, which is a very large Cohen's D. So it looks like not only can we conclude that oatmeal does better than drugs, it looks like it does better by a good bit. All right, so that's it for this example and this lesson. And, as always, please ask me questions anytime you have them. I always welcome questions. All right, have a good one.